Now that we have a slight idea about the underlying concepts of real and reactive power, let's dive a little bit into the math and figure out what are our equations for our real and reactive power of our circuits. And so let's start off with what is the average of sort of any time varying signal. So if I have some signal, that's x of t, and I integrate it over some amount of time, this is going to be my expression for the average, because I'm just going to integrate the signal over some amount of time. Now, I think we can all agree that if I have a sinusoidal system, and let's say that I integrate it over this amount of time, that whatever this positive value is here for this integration and this negative value for this integration is that the average of any sinusoidal wave over time is basically going to be 0. So as we integrate this over time, we're going to end up with 0 if our function is just a basic sinusoid. But remember, our equation for power had a couple of different forms, and so power was voltage times current, which is also equal to I squared R. And so our power here is actually non-linear. And what we're going to look at is what happens when our current is a function of time multiplied by the resistance. And so this is our sort of instantaneous power based on time that passes through some sort of resistor. And so now we can ask the question, well, what would be the average power of that signal? And so I'm going to apply the same integration across our average power, but it's going to be across our I squared R function. And in our analysis of AC circuits, we saw that all of our curves were sort of sinusoidal waves. And so for our definition of current, we will, as we've done with sort of AC analysis and phasors, we will show that our current and voltage functions are sinusoidal objects. And so instead of just being any old function of time, we're going to say that our current has a magnitude. And so if this was a current wave, it would have some sort of magnitude. And we'll call it a cosine function, and it's going to have some sort of frequency. And so when we plug in our values here, I will just replace our definition of I of t. So this would become Im cosine Wt, and then all of this will be squared dt. Now, as we expand all of this out, we're going to have Im squared and then a cosine squared, and it's become a slightly messy integration. But we can go back to our trigonometric identities and say that a cosine squared is 1/2 plus 1/2 cosine of 2x. And so we can rewrite our integration as this, as being 1 over t. Again, integrating across the time period. We will have for our, we'll pull out our constants, and I forgot to write r here. So r will come to the outside here. Our Im squared, which is a constant, is going to remain, and then we'll replace our expression here with 1/2 plus 1/2 cosine 2Wt, and all of this is again over dt. And what we're going to see here is that all of these elements here, as we go to integrate this, are going to be constant, and we'll eventually pull them all out. This right here is going to be a periodic function, so its average power is going to end up being 0, and we can drop it. And so in the end, what we find out is that our average power winds up being simply 1/2 Im squared times R. So our average power in an AC circuit for a resistive element is 1/2 the magnitude of the current squared. So if this is your current wave, the amplitude of that, the magnitude of that wave is Im, so Im squared times R. And we will transform this relationship a couple times, but this is our basic way to figure out what the average power for a real and resistive element is.